Let's see, 110, Lustre 2.5 performance evaluation, performance improvements with large I/O patches, metadata improvements, and metadata scaling with D&E. Hitoshi Sato is Project Assistant Professor at Global Scientific Information Computing Center, that's GSIC, of Tokyo Institute of Technology. He joined GSIC in 2009, has been involved with several HPC projects, including a series of Tsubame computers, especially in storage systems. Hitoshi, is that you? Come on up, ladies and gentlemen, presenting Hitoshi Sato. Thank you. Are you speaking as well?
Yeah.
Sorry, this is also Shuichi Ihara from DDN. Sorry, man.
No, that's okay. Thank you very much. I'm Hitoshi Sato from Tokyo Institute of Technology, Japan. Today we are going to talk about Lustre performance issues. The purpose of this project is basically designing for our new next generation supercomputers. So as a first step, let me introduce our current supercomputing facilities called Tsubame 2. Tsubame 2 is our campus supercomputer, and its product operation has started on November 1st, 2010. And thanks to commodity GPU accelerators, we achieved 2.4 petaflops per peak performance with only 1.4 megawatt per consumption. And at this time, we use NVIDIA's M250 GPU accelerator. But last September, we, by replacing the all GPU accelerator to NVIDIA's K20X, we improved the performance of the supercomputer. And here is the basic system overview of our Tsubame 2 supercomputer. Basically, we have over 1,400 compute nodes, each of which consists of 2 Intel Westmere-based CPUs and 3 NVIDIA Tesla-based GPUs. And we have 54 gigabytes of memory. And also, we have 120 gigabytes of SSD devices on other local storage for the computing nodes. And there are few fat memory nodes. And combine these computing nodes, these computing nodes are connected to the InfiniBand network. We use full bisection optical QDR-based InfiniBand networks. And part of the network is connected to the storage devices, storage systems. We use basically 3 types of storage systems. First one is home storage, and 2 others are parallel file system by using Lustre and GPFS. And we use these storages for various purposes. Home storage is, of course, used as home storage. It's for computing node. And we use also use the cloud-based campus storage services. And Lustre is used for the supporting conventional HPC applications, throughput-oriented HPC applications. And GPSS is also used HPC application, but this GPFS is configured with the using the hierarchical storage volumes, hierarchical storage management. So we use GPFS for big data applications with mostly lead I/O intensive applications. And we also use local SSD devices for application with fine-grained massive small I/O applications, such as checkpointing or temporal files. So we are planning to replace the existing Tsubame 2 supercomputer to next generation Tsubame 3 systems in 2050 or 2060 in time frame. So we have started several research works towards the Tsubame 3.0 supercomputers. First one is the interim upgrade to GPU replacement to Tsubame 2.5 by replacing existing NVIDIA M2050 to the modern Kepler K20X. We improved our supercomputer performance for 17 petaflops for single precision floating point performance and 5.7 petaflops for double precision floating point performance. And another work is Tsubame KFC project, which is a Tsubame 3.0 prototype system with advanced cooling for next supercomputers. So in the Tsubame KFC, around 40 compute nodes with 116 NVIDIA Kepler K20X and 80 in Ivy Bridge Xeon processor and FDR InfiniBand based computing node is submerged to the oil. So by using oil submerged system, we achieved very good energy efficiency performance and ranked the first position in the latest Green 500 list. So, but these activities are designed how to design the computing nodes. So storage design is also a matter for the next generation system. But existing systems, we achieve many storage problems. These problems are categorized basically two types. These two types, small I/O oriented problem and I/O concentration based problem. Small I/O problem is that parallel file system is basically conventional parallel file system is designed for the throughput oriented applications. So, and also many parallel file systems employs master worker configuration. So we observed many performance bottlenecks on metadata references. And moreover, recently there are many modern applications required to operate many I/O operations. So supporting high I/O operations is considerable, but we saw very, very low I/O performance around 1K or 10K in our system. And the next problem is I/O contention. Basically, file system is shared across computing nodes. So when the user's application with massive amount required to massive amount of I/O running such kind of application in the system, sometimes I/O contention is occurred, and performance we see the I/O performance degradation situation. The right-hand graph is the figure from our Lustre I/O monitoring system. The x-axis denotes the time, and the y-axis denotes the IOPS. Green line is the user's I/O operations. When sometimes users conduct many small I/O operations to the file system, but this situation sometimes disturbs other users' application. And sometimes these kind of massive I/O introduce suspended situation for the file system. So we want to avoid such kind of situation. So So considering these problems, we have several requirements for next generation systems. Basic requirement is, of course, we have to support sequential high I/O boundaries for traditional HPC application. But recently, there are many modern applications, such as network analysis requires the high I/O. So of course, we want to support this kind of high application with high IOPS application is important. And some application is a mixture of these two types of applications by configuring a single workflow. So basically, we need to consider these kind of applications. But these requirements is for application user point of view. But system administrator point of view, we want to reduce file system I/O facilities because unfortunately, our supercomputing system doesn't have enough budget and space and power. So there are many constraints. So we want to reduce such kind of I/O facilities, although we can achieve good performance by using a large number of I/O servers and drives. And besides that, we have several. We want to utilize new flash devices because we have already used flash SSDs as a local storage in the current Tsubame 2 system, but we want to exploit these new devices more efficiently and good solution. We need a good solution by combining existing files, the parallel file system. So summary of the requirement is as follows. So from this point, I changed the speaker and Ihara-san talked the Lustre benchmark results.
Thank you. I'm Shuichi Ihara, Data Direct Networks. So Sato-san mentioned about that we have started the core benchmarking, the evaluation, and the feasibility study for next generation system. So right now, we are working on the recent benchmarking with the recent Lustre 2X version. The benchmark is still not finished yet, still going on, but we collected some interesting data today, so we wanted to share some of the data here. Sato-san mentioned that for next generation system, not in general, so we have to reduce the number of the OST and the OSS. So that means, we have to maximize each of the OSS, the performance, or OST performance. We get a significant good performance number with a 4 megabyte RPC result, a 4 megabyte RPC. So we compare to the 1 megabyte RPC and 4 megabyte RPC result, RPC number. So improving the peak performance is also important, but the other side, how long keeping the peak performance is really important, really critical. That means we need to improve the sustained performance as well. Small SSD device. So this is not new, but it looks very new for the raster file system. So we started the raster on SSD, small I/O, the large I/O, and the metadata benchmarking. Started from today's OSS, the performance number. So this number is I present the last lag, the 2013. So the InfiniBand FDR, the most common the interconnect in HPC area. Today's the one single FDR InfiniBand link, we achieving the 6 gigabyte per sec. But so although So if we have enough storage device, and if we have the multi-rail, the InfiniBand rail configuration, so although the Lustre doesn't support the InfiniBand channel bonding today, but if we have the multi-rail configuration, so we can easy to break the 6 GB per sec, then we are achieving the more than close to the 10 GB per sec per OSS. So this is a reality. So this is the achievable number per OSS. This is another interesting data, benchmark number. So we tested the 4 MB RPC introduced Lustre 2.4. So we tested the 1 MB RPC and the 4 MB RPC and compared both results. So for OSS setup, the 280 Nearline SAS drives in the behind, then total the 14 client up to 220 for the process. So you can see the red color is a 4 MB RPC result. Then we can see the significant performance improvement for write performance, peak performance, as well as the sustained performance. You see when number of the process is increasing, so 1 MB RPC is going down quickly, but the 4 MB RPC result still keeping up the peak performance. Read performance is also the left side. The read performance, so when number of the thread is going up, so the performance is number a little bit going down, but the 4 MB RPC result, so always higher than 1 MB RPC result. So the system level, the 4 MB RPC is very help to improve the peak performance as well as sustained performance. This is tested the IOR, the fiber process. So this is more narrow down, then think about more degradation when number of the thread is increased. So this is an OSS standard point, the performance number. So we just set up the one OSS, then the 80 Nearline SAS drives, just 8 OST in behind. Then we have the 20 client, then up to the more than 906 process from using the IOR benchmarking from the client. So the blue color, this is a 4 MB RPC result. The red color is a 1 MB RPC result. So when we can, number of the thread is increased, so the write performance significantly improve the peak performance. So we are getting around about 9 or 9.5 GB per sec from the 80 Nearline SAS drives. But the 1 MB RPC results, so when number of the thread is increased, so going down quickly, then finally, but 4 MB RPC keeping up the peak performance. So finally, if we compare to 1 MB RPC result and 4 MB RPC result, so 4.5 times the faster 4 MB RPC, the result is 4.5 times faster than 1 MB RPC result. So this is a good, the sustained performance, the keeping up the sustained performance. So read performance, so 4 MB RPC and 1 MB RPC, it's a similar behavior, but the when number of the thread is going up, the performance is going down quickly, but 4 MB RPC only 30% the degradation compared to the peak performance, but 1 MB RPC result, 1 MB RPC, so more than 55% degradation, the peak performance. So still, the OSS, this standard point, the 4 MB RPC result, 4 MB RPC really help to sustain the performance. This is a more narrow down. So we tested the one OST device, then more concurrent access to the one OST, specific the one OST device. I set up the one OSS and the one OST, but we also set up the SSD device for OST. to compare to the spindle drive. Green color is the SSD number. We use a 20 client up to 640 the process to access to the one specific the one OST, so more concurrent access to the one specific the OST. The SSD is keeping up the peak performance always, so even the more than the 600 the process is from the client. However, the 1 megabyte of RPC on the spindle, so when number of the process is going up, so it's going down so quickly, then keeping up the 30% of the peak performance, which is not good. But so 4 megabyte RPC is still on the spindle drives, Nearline SAS drives. So it's the write performance keeping up 90% of the peak performance. Then after the more than 300 process from the client to the OST, the performance is going down a little bit. But the point is the read performance and the write performance. So 4 megabyte RPC, so even the more than the 600 process access to the from the client to the OST, so more than 70% the keeping up the 70% of the peak performance. So even the one OST device, the standard point, so 4 megabyte RPC is really help for especially the sustained performance. This is another benchmarking on SSD. So the previous benchmarking, the testing the SSD for large I/O, large sequential I/O. So this is a 4K random read on testing using the IOR to SSD device. So we use the two OSS and just set up the 10 SSD device to RAID 5 volume. Then using the 16 client up to 512 the process for total. So we use the IOR for this testing, but before the run IOR, so we create the random file with small block size. That means more extent of the file for the file per process and the single shared file. Then finally we run the IOR for read access with 4K. So result is quite impressed. So when number of the process is going up, so the IOPS for the 4K random read is going up so linearly. Finally we achieve the more than 500K IOPS for random read 4K for the 4K random read file per process. Then also we also achieved more than 450K IOPS for single shared file for random read. So we didn't much expect the high IOPS with Lustre. However, so this number is very encouraged to Lustre perform the SSD well. So we need to more investigate it, but so it looks like the number is quite nice. So quick conclusion on Lustre with SSD. So Lustre today, OST pool the future. So we can make the specific OST pool with SSD, but SSD change the behavior of the pool because so seek is no issue on the SSD. So we think a little bit the application scenario, the OST pool with the SSD. So because so one of the example, if application really want the very consistent the performance and independent I/O, or if application does so a lot of the concurrent access to one specific OST or the SSD device, that SSD more help. And also, if application really want the high random access with a small I/O, it's also significant the performance improved with the SSD. So with SSD, so bottleneck is not the device itself, but we need to think about the considering the RAID array or RAID software on the top of the SSD device of the file system. So finally, we can achieve the high IOPS for random read with a raster file system. However, this is not, so one of the limitations is the metadata workload. So this workload is only the high IOPS for the single shared file or the multiple the file on SSD, not the small file I/O. So SSD benchmarking we just started, so we need to more investigate it. So the final benchmark results, so metadata performance improvement. So as you know, the discussion there, so we see the significant metadata performance improvement and since Lustre 2.3. So there is the performance comparing. So one is the compared to the Lustre 1.8 and the Lustre 2.4 for the single shared file, the metadata operation. The other side, metadata, using the single metadata server and the multiple metadata server with DNE. So overall, the metadata performance improved significantly, especially compared to the 1.8. So the metadata operation is really improved. So the quick conclusion for metadata performance. So metadata performance is significantly improved for shared and unique directory and both from the Lustre 2.3. But SSD may help to improve the metadata operation, but the impact is limited because so metadata operation, the MDS, so really want the latency, not IOPS performance, not IOPS device to SSD itself. So important consideration, so metadata benchmarking, so really need to be careful about the hardware, the configuration, as well as the raster itself. So for example, the hardware setup and the BIOS configuration is really sensitive for the metadata performance impact. Okay. Then finally, so another the consideration. So if we think the metadata benchmarking from the small number of the client, so since the single client metadata performance is limited, so we think about how we can saturate metadata server from the small number of the client. Then finally, so a quick summary. Lustre today's, so as I showed some benchmark result, so finally a little bit no time to the more detail, but so we see the significant performance improvement for the OST standpoint and the metadata standpoint. Then much better the spin load efficiency. So we are now getting the physical device limit. Then in the future, the client performance should be showing up for especially the small file or random performance, not only the server side. The alternative scenario, so SSD device, so we now testing the SSD on the raster. However, we need to think about the combination of the raster file system with the SSD device, nearline the SSD device, more like HSM or kind of the migration, the staging the solution with SSD. Thank you.